It's my pleasure to introduce today's speaker, Jud Partin. So as everyone knows, Jud is a research associate professor at UTIG, and his research centers on understanding climate variability and change, both force and natural variability, using geochemical records of paleoclimate archive, such as corals and stalagmite. And he also compared those data to climate model simulations. So Jud received a bachelor's degree in chemistry from Citadel and master's degree in physical chemistry from the University of Southern California. And then he had a few years of industry job experience and returned to graduate school and receiving PhD degree in Earth and Atmospheric Science from Georgia Institute of Technology. So he initially joined UTIG as a postdoc and then got promoted to the current position. So both Jud and I study tropical climate variability, such as El Nino, La Nina, and the tropical Pacific decadal variability. And then I really enjoy collaborating with him over since I came to UTIG in 2011. So what Jud impressed me most is his fearlessness to address like important scientific question. And he was a main driving force in getting unprecedented coral data from the last glacial period, and which is critical to understanding the future changes of El Nino. And I also want to note that Jud is a very caring advisor to graduate students, and his student, the student who was mainly advised by Jud just finished PhD this month. Rob is sitting in the front. So congratulations. So I stop here, and then Jud will tell us more about ancient El Nino in your warming.
Nice. Thank you, Yuko. Yeah, and a round of applause to Dr. Rob. He's graduating. Yay, Dr. Rob. Nice intro. So I don't need to say anything else other than I'll be telling you guys today about El Nino. This is a home crowd. This is the first time I'm giving this talk, so it's going to be rusty. So it's good to give it in front of the home crowd, which is nice. All right. So first off, this is a huge endeavor. I'm trying to go through all aspects of this research. So if you came here to hear about the specifics of the climate model or something like that, you won't get any specifics today, but I'll try to give you a more general overview, which is good for a Friday in the last seminar of the semester. But it's a huge endeavor. And in the middle is, for this project, we're trying to study El Nino, the El Niño-Southern Oscillation. And I'll tell you what that is in a minute. But first, the people. So there's a lot of aspects to this. The first is the land drill and the field work, which was a huge endeavor undertaking. I'll kind of gloss over some of that. I'll show you some pretty pictures, but it really was a couple years in the making. And we have a large contingency of people from Vanuatu that we still collaborate and involve with the research, parachute stuff going on here. And Eddie Wheeler, our tech extraordinaire who built the drill, did amazing work. So after we go to the field, get the sample, we then have to date the samples and subsample it. And River Shen out at National Taiwan University is doing an excellent job dating all of our samples. We then run some geochemical analysis to provide us with some paleoclimate proxies. And we have a super team running computer simulations. Actually, walk out the door to the left. You'll see Lone Star 6 right there, where we're running the computer simulations. And then after we do all that, we have to do some high-level data analysis to compare the models to the geochemical analysis and hopefully arrive at some understanding of El Nino. Feel free to interrupt at any time. I really don't care. So first question is, what is El Nino? And for those of us who were around in the 90s, it was a huge deal. It was pop culture because 97 and 88 El Nino was a really big event and caught everyone's eyes. It even made Saturday Night Live. R.I.P. Chris Farley. So El Nino is usually written as ENSO, E-N-S-O, and it's defined by the sea surface temperatures inside of this box, the Niño 3.4 box in the tropical Pacific. So they just divvied up back in the day the Pacific into the 1-2 box. Well, they couldn't even decide there. Niño 3 and Niño 4. And then it turned out this region right here between 3 and 4 was the sweet spot where if you know how those sea surface temperatures are changing, or if we know how the temperatures are changing, then we kind of know the state of this phenomenon known as El Nino. They last about 1 year, an event, and they occur every 2 to 7 years, approximately. And this is what we call interannual timescale. So if you hear me say interannual, it's like from year to year. So it's not from decade to decade. So it's kind of interchangeable every 2 to 7 years. They begin at the same time of the year, right around March, April is when a little baby El Nino or La Nina starts to form. They grow through the boreal northern hemisphere summer, June to October, and they peak around December, which is why it's called El Nino, because Peruvian fishermen back in the day noticed there's changes in upwelling in here and nutrients, and they were relying on some little fishies to live, and they realized some Christmases there weren't any fishies, and they were like, baby Jesus, help us. And so El Nino, baby Jesus, hence the name. And this is a phenomenon where the ocean and the atmosphere actually interact and feed back on each other to make the event happen, grow, and then finally to end the event. And way over here in the Western Pacific is a bunch of warm water called the Western Pacific Warm Pool. That's normally over here. And sometimes the ocean and the atmosphere kind of get together and interact to make this warm water come over here to the Central Pacific. And if that happens, then we have an El Nino event. Sometimes the winds will strengthen and this warm water kind of gets even warmer over here, it gets colder over here, and this normal condition gets amplified, and that's the opposite. It's a La Nina event, and so it's an amplification of the normal conditions. Videos focus on speaker only. Thanks, Akert. Oh, it went away good. All right. So this is inside that Niño 3.4 box, the white box. These are sea surface temperature anomalies, so the departure from normal, what would happen during an El Nino event. And this is a composite of 3 big events, 72, 82, 97. And this is going to be during the peak. So it peaks in December time, Christmas time, baby Jesus. And so we're looking at just the peak of the temperature anomaly for these 3 events. And these 2 locations I have marked here, Vanuatu in the Southwest Pacific and Christmas Island here in the Central Pacific. I'll show a bunch of data from there during the talk, so I wanted to point it out now. And you'll see these again and again. So over here is Vanuatu and Christmas. And so you can see here a big, huge anomaly of warm water spreading all the way across. And a lot of times when you look at the stuff, you don't appreciate the size of it until you start going to a global map. And so here's that same map of sea surface temperature now overlaid on a global map. And this temperature anomaly, even though it's like only a couple of degrees, is larger than the continental United States. And so when that happens, global climate really listens to that and things start to reorder. And most importantly for us humans, now the ocean, the temperatures matter, and I'm trying to minimize that. But for us, there's regions of drought and flooding. And so over here in brown are regions of drought, and then in green are going to be regions which have anomalously more rainfall. That's why we really pay attention to that, because drought, crops die, people need food, and quite the opposite, flooding, bad too. And here in Texas, we pay attention to this because the atmosphere stability, kind of vertical wind shear, so the lower levels versus the upper levels, called the wind shear. And during an El Nino event, this wind shear over here in the Atlantic is stronger, and it rips a hurricane apart. So for us in Texas, if we it's an El Nino year, generally we can expect less tropical storm activity. Now the opposite is going to be La Nina, and this has nothing to do with the female baby Jesus. It was just the masculine and feminine in Spanish. And so it's the opposite, where we have anomalously colder sea surface temperatures in the tropical Pacific. So here's that Niño 3.4 box, about 1.5, 2 degrees. But again, it's a big, huge area, and it's a whole lot of heat that changes. And so there's that same sea surface temperature anomaly map on the tropical Pacific. You can see it's the same size. And again, we have, what do we got here? Now we have some drier areas in brown and some wetter areas over here. So during La Niñas, we had that triple La Nina a couple years ago here in Texas, and it was an extended drought, if you guys recall. And so over here is going to be Tejas, where we had a whole bunch of drought with triple La Nina. And I'm concentrate on Texas because we're in Texas right now. If I gave this talk in another place, I probably wouldn't. But at any rate, so tropical storm activity tends to increase more during La Nina years, and we have more tropical storms because that wind shear lessens a little bit, and it allows the growth of these tropical storms. And so we see tropical storm activity, and here's the, I took a shot of sea surface temperature anomalies during November of 2020, just a 1 week kind of average. And you can see that blue region here. You can even see it in the raw sea surface temperatures. This is the anomaly, here's raw, where this is always that warm pool. And sure enough, 2020 was quite the year for tropical storms. We went into the Greek alphabet. Here's a delta and a beta. So it does impact our lives here. But the big kicker, while we look at La Nina here and it's a big deal, these extreme El Nino events are the real kind of change perturbation to the climate system. And so here's going to be the change in global GDP, so gross domestic product, for these big events. This is going to be the 2015-16. And so we see here a reduction of about $4 trillion over 3 years. The strongest event was the 97-98, and we're looking at a $2 trillion reduction in global GDP. So they're hammering the Earth pretty hard, and you have to pay attention. And this doesn't even get into the lives lost as well. There's definitely societal impact. But just in terms of raw dollars and getting politicians and people's attention, this is a pretty big deal. And so these climate models that we'll be talking about are run into the future, and they try to estimate, hey, how's El Nino going to change? Is it going to get stronger? Is it going to get weaker? And there's a range of scenarios going from a little bit of warming to a lot of warming. And you can see here this big wide range of cumulative global GDP loss for the next century. And you can kind of see it here in a distribution form. But in the most part, a lot of the models are saying, hey, we're going to lose a lot of global GDP as we go into the future. And really over here, you can see these long tails. And these tails are driven by these extreme El Nino events that I was just talking about, 97, 98, 2015, 16. And so these extreme events, when they do happen, really do hammer global GDP, lives lost, really big deal. And so we want to know more about them because they're a pretty big deal. And so the projection loss is anywhere from like 14 to $84 trillion, which is a mind-boggling amount of money, and a very wide range. So we'd like to know more about how they would change in the future in order to A, prepare, and then B, try to mitigate any changes or any impacts from them. And then C, we're going to lose a lot of money irregardless because we're not changing our ways. All right. So in the top, this is going to be the observations of sea surface temperatures over time. These are monthly values. These are anomalies, so departure from normal in the Niño 3.4 region, going from calendar year 1900 up to 2020. And we can see these extreme events popping up here. And there's been 4 big events. There's one back in World War II. Data's kind of spotty. The war was going on. But it seems like it was a big event. But over here, you got 72, 73, 82, 97, 98, and 2015, 16. And they're popping up above this 2-degree line, which is our threshold for an extreme El Nino event. And there's been 4 in the last, say, 40 years. And so we found out that trying to say in the year 9,722 years ago was an El Nino event is really difficult with dating errors and geological uncertainty. So we shifted our target to try to say like, hey, these decades had stronger and weaker ENSO. So how do we do that? Well, we're looking at the standard deviation of this guy down here in 30-year bends. So you take a 30-year window, you take the standard deviation, you move it, you move it, you move it. And so this is going to be the standard deviation of those 30-year windows. This red dot is the standard deviation for this window. And you can see with all these big events, it's quite high. Over here, you have very few events, and so the standard deviation is kind of low. So this is going to be a period of lower ENSO strength. And then here we have our period of higher ENSO strength with these bunch of extreme events. Now I've plotted a range of products. This dark one up here, this is going to be the NOAA product. Shout out to NOAA while you're still there. And then we got HAD products, which is out of UK, Kobe is Japanese, and then independent product. And for the most part, they agree. There's a little outlier here. But when you go back in time, there's a spread because there's less data. And so there's more uncertainty when you have less data. Shocker, spoiler alert. So prior to about 1950, there's not many observations, really. So we then turn to the paleoclimate record, which is where the geochemistry comes in with the corals. So here are going to be those two sites I told you about before, Christmas Island in purple, Vanuatu in UT orange. And they're getting very similar results where you have more active ENSO here, less active ENSO here. And I'm sure you're going to be like, oh, it doesn't agree pretty much here. When we go back in time, we're not trying to reconstruct these wiggles. We're trying to reconstruct this forced change. So do you have a whole period of a lot of ENSO activity and a little bit of less? We're not so concerned of the decade to decade and the year to year when we're looking at the forced response, because that's more of that natural variability as the climate system just moves energy around. We're looking at more of that forced response, the larger signal, which the corals do get. Oh yeah, there's a trend. Nice one. Okay, and we know in the future, CO2 is rising. We're not mitigating too much. So as CO2 goes up, the global temperature also goes up. And so we want to know, how is El Nino going to respond to these higher global temperatures driven by anthropogenic emissions? And long story short, we don't really know because we don't have a time machine. So we're trying to use computer simulations. And really, it's no shocker. And so it can get stronger. There could be no change, and it could be weaker. And we could gamble and roll the dice and be like, well, whatever comes, comes, and we'll just deal with it and be fatalistic about it. Or as good scientists, we can try and form some sort of scientific method to attack it and look at it, and which is what we're doing by using these computer simulations and coral models, or coral data. So our approach is we're going to take these climate models that are used for the future projections, force it with geologic boundary conditions going back in time to the last ice age, using as best as we can what we think the forcings were, and then compare that climate model output to coral climate reconstruction, with the hope that if the model does get things right in the past, maybe we can trust it more for the future. Okay, so there are almost as many models as there are wealthy countries, and everyone wants their own model. So all of these flags represent country flags who have models which are fed into this intermodel comparison project. So MIP is intermodel comparison project, where this is the kind of modern climate, and PMIP is the paleoclimate, but it's a global effort, and there's a pile of them. I'm not a politician, and I'm not on this stuff, so I can say they're not all created equal, and some are real turd buckets. Some are really good. And they went back to about the year 2000, back in the day, and every 4 or 5 years, they have these IPCC reports. You can see them released. So one came out in 2000, and they took all the climate models at the time, combined them all together, and they got this big spread. And 2000, they used instrumental data to force these climate models. And you can see they get these wiggles kind of really good. You get a volcanic eruption, you get some El Nino. The climate models do really well. Into the future, it's kind of this flat line, the black multi-model mean, with a huge spread around it. And these ups and downs tend to be these big El Nino events. And the climate models don't have enough capabilities to predict these things years into the future, much less months into the future. But when you look at the multi-model mean, it's going up. The observations, no matter which product you use, the colored lines are the observations, they're going up into the future. And so the climate models are doing a really good job. And this is in the year 2000. These climate models predicted, these are older versions of the climate models too. They got fancier bells and whistles now. But they're predicting pretty good an increase in global temperature, hitting right through the middle of the observations. And so this forecast was from going to here, and they're hitting right through the middle. They're not getting ups and downs because they don't get the natural variability too well. But the global temperature, they're doing a really good job. And so they're forced by a couple things, greenhouse gases and aerosols. Those are going to be the two major forcings going into the future. And so everyone knows about greenhouse gases. You got CO2, methane. There's some couple other ones, NO2, N2O, SF6, whatever. But these are the big two 800-pound gorillas in the room. And aerosols are going to be little particulates that interact with the atmosphere and may reflect some light or form clouds. So here is your stronger, no change, weaker, where this is your alphabet soup of models. And many of them are those countries that I showed you earlier. So you have, here's the US, you got Japan, there's NASA, there's going to be Australia, the French, UK. And it's all over the map. 3 up, 3 down, end of an inning. You got really no information here. The multi-model mean is no change. So how can you use this to prepare for any sort of future scenarios? It's pretty no good. Here's even more models. It's like, okay, well, more must be better, right? No, more isn't better, better is better. And so even more models, instead of alphabet soup, we have a variety of numbers here, all representing different models from different countries. And they're not all created equal, and some are better than others. And again, stronger, weaker, no change. So we're left with, again, prepare for everything, which still isn't too useful. So there's no real consensus on future ENSO projections. Well, enter the paleoclimate. What did ENSO do in the past? The past climate forcings are much more varied. They're larger. They're over a whole bunch of different things. So over here, we still have greenhouse gases. During the last glacial maximum, greenhouse gases were lower. Temperature was colder. And they formed ice sheets. And so these ice sheets have not only an albedo or reflectiveness, they also have a size, which is included in the climate model. When you start going back tens of thousands of years, you start having orbital changes. These are included in the climate model simulations. Ocean circulation changes with AMOC. Those of us old enough, this isn't pop culture anymore, but there's the Day After Tomorrow movie where the ocean circulation shut down, and of course the world froze in 3 days because go Hollywood. And then there's sea level, and our collaborator Pedro Venezio, he did an excellent job with the climate model I'll show today, CSM1, where he actually went in almost grid point by grid point. And this is an area over here. This is going to be Australia and Southeast Asia with Borneo and Papua New Guinea here. And he kind of went in grid point by grid point through time and looked at how these different pathways opened and closed as you change global sea level going from the last glacial maximum with lower sea level to today after you deglaciate, melt the ice, fill up the bathtub of the ocean, and start to open up these pathways through time. So these time slices I'll show you actually have ocean circulation changes due to sea level included in them. So we're really trying to capture as well as we can what we think the state of the Earth was at the time where we go collect any coral which had grown at that time. All right, I'm going slower than I thought. So I might have to skip a few. So CESM 1.2 is the model we're using. That's the Community Earth System model 1.2. It displays a really realistic ENSO behavior, and this is how you can objectively judge if a model is good or not for ENSO projections. If it don't look like, if the observations and the model output don't look alike, then you can be like, well, maybe it's not good for this. Maybe it's good for something else, but maybe not for ENSO. So up here is going to be annual mean surface temperatures for observations and for the model. And for the most part, they look really well, where you have the Western Pacific whirlpool over here, the cold tongue with the upwelling. And these are going to be the sea surface temperature anomalies that I showed you before. And this is going to be observations where we're looking at El Nino, so that warm changes in sea surface temperature. And over here is how the model represents El Ninos. And I should point out, it's an emergent phenomenon. There is no El Nino button. You set the model up, parameterize what you do, million lines of code, go over to Lone Star 6, hit go. And when you do, the model starts bouncing around and produces its own El Nino and La Nina events. It's pretty amazing. And this particular model, it's a lower resolution model, so it's affordable, and we can do these really long runs in order to get good statistics across these different time periods and do a whole bunch of different time periods, because these are pretty expensive, and we have nice collaborators over at Tech next door. All right, and these time slices, we take any point in the timeline, and we can branch off and run the climate model based on these different climate forcings over here on Lone Star 6. And we can prescribe it with any mixture of these different things, given the period of time that we want to do. So we're going to do 15,000 years ago, we're going to do 20,000 years ago, 17.2 thousand years ago, whatever. And we can run it for hundreds, if not thousands of years and get really good statistics on how ENSO responds to those forcings in order to compare as best as we can with the paleoclimate data. And here it is. So this is going to be a pile of computer simulations distilled into one plot. Each one has anywhere from several hundred to 1,500 years. And time is going this way. So we have 2 times CO2. This will be the future. 0 is going to be pre-industrial. So how the Earth was about 1850 before we started doing what we're doing. And we go back in time, 3,000 years, 6,000 years, 9,000 years. And then we get back over here to the last ice age. On the y-axis is going to be ENSO strength. So higher, stronger ENSO, down, weaker ENSO. And CESN 1.2 shows stronger ENSO at 2 times CO2. So in that alphabet soup I showed you, it would be a little bar chart going up to stronger ENSO. And over here during the last ice age was weaker ENSO. And pretty much at 15, it died, like according to the model. It's like there's hardly any variability about the hundreds of years, and it's really low. So it's a great target. This is how it's going to look in a PDF form. So we're looking at the different slices, and the wider it is, the more El Nino. So we're looking at a sea surface temperature anomaly. And so these are going to be the big El Nino events over here, big La Nina events over here in the Nino 3.4 region. So remember that region gets warm during El Ninos, cold during La Ninas. And we can see this widen. And so we can see this is the same data here in PDF form versus, our little box and whiskers. So same data represented a different way, showing that indeed here ENSO is weaker at 15, this guy here, and 2 times CO2 is going to be the pink. And this is driven by these extreme El Nino events, these really costly events. So this is the percent of extreme El Ninos, where we got almost half the El Nino events are extreme at 2 times CO2. They're just like hammering, just like bam, bam. Huge variability. And we have high ENSO strength driven by a high number of extreme El Nino events. Conversely, over here during the last ice age, when ENSO strength was lower, we have fewer number of extreme El Nino events. So now we have a nice framework presented by this model that we could test with paleoclimate data. Yeah, strength driven by a large number of El Nino events. And so you can take the model because the model has all the different fields and you can do a bazillion calculations, and smart people like Yuko and Pedro can go in and pull it all apart. You can calculate, this is going to be named after a scientist who kind of pioneered the work in the tropical Pacific, Bjerknes. And they named it the Bjerknes feedback. And that's that interaction between the ocean and the atmosphere. And so as the ocean and the atmosphere kind of conspire and get together and start interacting more, that interaction strength goes up at the 2 times CO2 when you have more extreme El Nino events. So they're actually conspiring to work together to feed back on each other. Conversely, over here during the last ice age, that interaction, the connection between the atmosphere and the ocean kind of goes a little down. They're not conspiring as much. And you can even see it in the monthly evolution of these events. You see like, hey, during June, July, August, when it's growing over here to the peak, we have a huge feedback. So this is that interaction, that conspiration between them, conspiracy. And we have more conspiracy here, less conspiracy, for lack of a better word, feedback here. And so then that helps the event grow, blossom into a big extreme El Nino event in the model. And so that kind of controls the number of extreme El Nino events, these costly events that are happening. And the background state of the tropical Pacific is also kind of conspiring, not only the feedback, but it's getting off on the good foot or getting off on the bad foot. And so down here during the last ice age, we can look at the edge of the warm pool, this line, or the strength of the trade winds, or the mixed layer depth. And that's kind of how you're setting up the tropical Pacific. And when you start to move that warm pool edge way over to here, we're looking at the map way over to the west, then the warm water has to get over to the central Pacific. And the further you move it over here, you're kind of starting off further to the west, and you got to go even further. And so you're starting off kind of like in a bad spot. Then you also have the feedbacks, which are also weaker. And so you just really never grow into these giant extreme events. So the trade wind strengths control kind of the edge of the warm pool and how deep the mixed layer is. And if you get a big pile of warm water way far to the west, it gets really hard to move it over to the Central Pacific where it needs to reside to be an El Nino event. And so everything's kind of working together in the model to do that. And so this is what I was just saying earlier. So here's that warm pool. So if the edge of the warm pool is even more over here, makes it even harder to get to the central, right? That warm pool. And then this water is even deeper because you're blowing even more water over there with the trade wind strength. You deepen this area, you have even a bigger body of warm water. It's harder to move over there. And the coupling is weaker. So that all adds up to either fewer extreme El Nino events and weaker ENSO during the last ice age. And here it is in kind of picture form. I just said all this. You can go to the publication and read more about it if you want. But it's kind of like the the cycle. So the trade winds start to relax, the ocean water starts to move, which makes the winds weaken even more to make the water move even more. And so that kind of cycles from March into June into December during the year to form the event. During the last ice age, there's this weaker coupling, so the weaker feedback. And you're starting from a boundary condition, which is even harder to initiate these extreme, or any event really. And conversely, 2 times CO2, you have stronger feedback. So that edge of the warm pool, instead of being way over here to the west, that edge of the warm pool is a little further to the east, so it doesn't have to go as far. And you get a stronger coupling between the ocean and the feedback, so you're starting from an easier spot. And the conspiracy is, not conspiracy, but the interaction is acting to grow them into events. In the interest of time, I'll just mention that there's some really nice marine sediment core data from the Central Pacific near Christmas Island, where they're looking at individual forams. And it shows weaker ENSO during the last glacial maximum. So here's a data point, which is from paleoclimate data using foram analysis to show that indeed during the last glacial maximum, this data supports the hypothesis of the model, which suggested weaker ENSO. Marine sediments are excellent archives, but all archives have strengths and weaknesses. There's no one best archive. Some of the weaknesses of the marine sediments is that they get bioturbated, and the sedimentation rate may be low, so you don't have a really high temporal resolution. There's also difficulty with individual foram analysis separating seasonal from interannual variability, just due to how the sediments are deposited. And at this location, there wasn't a lot of sediments between 21 Ka and present, not as much, with that fine resolution to resolve that 12 and 15 Ka. So we turn to corals, yay! So they are excellent recorders of sea surface temperature and salinity. They're living in the ocean. They're making their skeletons out of the seawater. We can date them with uranium-thorium dating, get age errors of about 1%. And we can separate the seasonal cycle from interannual variability. And I just remembered on the way in, I didn't put in here, they can resolve those extreme events as well. That would be a huge strength, where the individual forams have a little more difficulty resolving an event. But we can with the corals because they're monthly resolved, which is kind of a subset of this strength. Now, the weakness is they're only found near land. So these sediments are all over the ocean floor. You can go out and core and you can get them from all over, which is really great, which is why they've been such a powerhouse proxy. Corals, they only live for about 300 to 300 years-ish. Sometimes these giant ones may be like 400 or 500 years, but that's about it. They grow themselves into the surface and die out, and the reef gets covered up. And so you get these windows all through time, if you're lucky enough to find these corals. Because during the last deglaciation, when sea level is 120 meters lower, they're growing close to the ocean edge. You deglaciate, you cover them up, so you need to use a drill ship. And it's also a proxy archive of climate. And so we spent a lot of time developing a proxy system model to see like how the coral is growing in order to remove some uncertainty from the coral and concentrate more on the environmental variable. So it's going to be your weaknesses. Luckily, though, we were pretty good at finding these corals. So when you think of a coral reef, you think of a really nice, when I go scuba diving and see some turtles and stuff like that. And these are all really nice, beautiful corals. Here's going to be a branching coral, but none of these are the ones that we're going to be using for climate. Instead, the ones we're using for climate are these big, massive corals. So here is a young Dr. Fred Taylor. Jamie took this photo. This is in Vanuatu. And this is big dome. It's a massive coral. And it's much like the branching corals, but instead of the branches having seawater in between, the outward growth of those branches meets the other branch, and it grows together and forms a big, massive stuff. If the extension rate, if it was growing faster outward than sideways, then you'd have seawater in between, much like one of these branching ones down there. But that sideways extension rate fills it all in and forms these big, massive corals. So these ones we're looking for paleoclimate. And this would be a particularly large one. Just keep that in mind for the fieldwork stuff. So you can see a human there. That's a smaller one. Maybe like from here, the edge of this table to over there. So for the people in the Zoom, that. And they're a passive recorder of the conditions. So as they form their skeleton of calcium carbonate, they start incorporating in either different isotopes of oxygen, 16 versus 18, based on the temperature or the salinity, or a ratio of different metals in the skeleton, like strontium, calcium. And so we spent a lot of time to develop a way to connect the paleoclimate model with the geochemical data. Because in the end, we want to test that hypothesis that we just told you about CSM 1.2 with this coral data. And so we developed a proxy system model, which kind of connects the two by taking the paleoclimate model output, perturbing it, monkeying it around to make it look more like a coral in order to compare with the coral data, to try to compare as much as we can apples to apples. So we call that a pseudo-coral. So if you see pseudo-coral, that means we took model output, ran it through another model, in this case, a proxy system model, in order to compare it with the geochemical data. So when we take these big massive corals, we'll usually go with the drill core, bring a core up, and you can see here, these bands here, these are individual years. So you have a summer, winter, even in the tropics, you have a cold, warm. And so you can see these bands much like a tree ring, and we follow these bands down, drill along it. This is going to be on the micro mill in the lab. So we'll subsample it, and I don't want to poo-poo on other people, but it's a certain good skill to stay along this growth axis. Because if you don't, then you're going to be incorporating other forms of uncertainty in the archive. And so I'm not going to say everyone does it, but there's some people that are not so meticulous as we are. But I'll say we're really good. I'll stay on the positive. And we're really good at subsampling these the right way to get a good record of climate. And you can run it through different machines. And so this is the geochemical aspect. Cal Septorumli and Chris Maupin at AM, who's not there any longer, but they did a lot of these geochemical analysis for us. What's up, Cal? Thank you for the great data. Strontium calcium and O18, where these are different components of that coral skeleton, which give us climate. And in the interest of time, you got to trust me on that one. All right, so we've done a whole lot of work here on this proxy system model to not only calibrate going from a geochemical to an environmental variable, because that's what the climate model gives us, but we're also incorporating how the coral grows. And so there's differences in growth rate and subsampling, analytical error. So we combine all that in, and we came up with what we think is one of the best proxy system models out there to go from a climate model to a coral. Shouts out to Allison Lawman, that was part of her PhD. She's at Colorado College now, did fantastic. Okay, so just to go back, I don't know why I put this in here, but we're looking at El Nino again. Right. So this is going to be coral data from this location here, Christmas Island, the triangle. It's one of the best spots for coral data, hands down. Unfortunately, there's only about 3 islands, well, really 2, because Palmyra is outside of it. There's 2 islands in this whole freaking giant box of bigger than the US. And you need land to get a coral. So there's really only 2 spots to get a coral inside that box. Keep that in mind. So this is the best place to go get it, the most accurate representation of El Nino. And this is all previous published stuff. And so the dots here are going to be the coral data. This is going to be that climate model output from CESM, where we took the grid point nearest to that island, ran it through the proxy system model, tried to compare it to the coral. This was just the publication of the coral data, the science, like big time, highly variable. There's really no signal. And they're only going back to about 6,000 years ago. And down here is a record of sea level, where this is going to be kind of current sea level minus the global warming aspect. And you go back in time, and as the Earth was glaciated, you had a lower sea level because that seawater is locked up in land ice, lowering the level of the bathtub. And you can see there's not many coral data from before when sea level was high, because those are all offshore. Because as you lower the sea level, you got the flanks of the island, so you need a drill ship to go out there. And I don't want to knock on the drillers. They're really good at drilling sediments, but there's a whole division in drilling between soft rock and hard rock, and especially carbonates. And I'll just say that the recovery wasn't so good. And so the drill ship for the last 50 years has had a lot of trouble recovering these glacial corals on any offshore drilling on any carbonate platforms. It just, a lot of times, hey bro, how deep you go? And it's like, it's not how deep you got, it's like, did you get the good stuff? And if you recall from CESM 1.2, that this was the largest El Nino signal. So pretty much those corals are from here that way, where the signal of that force change is really small, and the base signal is back here. And even though it's like one of the best spots to study ENSO, it's really hard to get corals from when we think the signal is largest. So then that brings up Vanuatu. Oh, why go to Vanuatu? Well, turns out our illustrious Dr. Fred Taylor has spent many a decade out there. And just to refresh you from where Vanuatu is, it's going to be over here. And there's two converging plates right here. You can see this plate going under the other one here. And we're really concentrating on this village of Tanavusvus. Shouts out to Chief Cal. And we went in 2019, back in 2023, drilled all along the coast right here with the drill that I'll show you in a minute to try to recover these glacial corals. And it's a convergent area where you have a guyot subducting underneath one plate going under the other one. It's pushing it up. And because it's pushing it up, the tectonic activity is bringing these corals up to the surface. And indeed, these are the calculated uplift rates based on ages of corals during the mid-Holocene when we know what sea level was, so we can separate the sea level component from the tectonic component. And this is going to be the uplift rate in millimeters per year, going from 1 to 7. And I thought about a good graphic where I could just do the calculation and show it to you, but you can do it yourself. It's really easy. If you take 7 millimeters per year times 20,000 years, which was the last glacial maximum, it's going to be 14,000 millimeters in 20,000 years, which is about 140 meters, which is pretty much where sea level was during the last ice age, about 120 meters lower. So they formed at the surface, and then tectonic activity has brought them up to the surface again. And so we're more able to more easily access them. And even if you go over here, we hit the last glacial maximum corals at around 16 meters depth. Even if you drop 2 millimeters per year, that depth goes to 45 meters. So you have to drill 3 times as deep. And it's an exponential amount of time drilling deep versus more holes. The deeper you go, it takes much longer. It's not the same. Here's a nice graphic to display what I just said. So 20,000 years ago, you have the coral reef forming. Sea level rises during the deglaciation, but this land is getting pushed up by that tectonic activity, bringing those corals up to the surface. So we put our drill rig up there and have to drill only a shallow amount to actually reach these glacial corals. And I will say we're way better than the drill ship on carbonate recovery. I've looked at their logs, crushed it. Here's a nice little model. It's called CLEX, where you can say, hey, given the uplift rate of the island and the change in sea level, we'll try to model what the stratigraphy would look like in a cross cut of the island, where this is kind of like, an erosional feature where, no island looks like this. It's got all messed up and jagged coastline, where we have stuff up here 14, 15,000 years ago. And then this is going to be like the land surface, sea level, and then we drill deep down here. So we're trying to target down here to get these ice age corals. I'm speeding up now because it's 11:15. And we get a lot of pushback because people say, oh, you're going to Vanuatu, it's not in the center of action, it's not Christmas. So we've done a lot of work to show that indeed interannual variability in Vanuatu is related to ENSO, because you can't have it both ways. ENSO can't be a global phenomenon that wrecks, the world economy and not affect Vanuatu. It's got to affect it, right? You can have both. And so we've done a lot of work to show that interannual variability changes there do reflect changes in ENSO. Skip that. You have to trust me there. You can read the papers. But first, we had to build the drill. And so here's 2019. We tested out at the Texas Observatory. That was version 1 of the drill. Version 2 of the drill, we tested it again at the observatory, but this time we brought the whole admin staff out there. And I got to say, there's no way we could have built this drill without the admin staff. They were fantastic. It was a big endeavor. It took years. Shouts out to Eddie. There he is to build the drill. So here's the drill. And we set it up, and the admin was able to drill, and we actually recovered core at the observatory because it is that portable and easy to use, and we were able to execute it without a $500,000 a day drill ship. So we packed it up, put it on a container ship, and then this is how we get the drill out there. Like, you load it up in 4x4s and you're taking it out to this remote spot because that's where the uplift rate is highest in order to access these glacial corals. So it wasn't Dylan over there. He knows about this fieldwork stuff. It's not easy, but you got to go where the stuff is. And so it's highly portable. And I mean, the people there are amazing. There's Chief Cowman. I got adopted into his family the last trip, so he's my brother now. So I mean, it's highly portable. We can carry it wherever we want, set it up, and go to the most remote places where we think these corals are in order to find them, because we want to test this climate model. So we put the portable and ultra portable We did great in 2019, recovered tons of core, like in terms of like recovery rate. I don't know, I didn't calculate it exactly. It's like probably around 70–80% for carbonates, which is amazing. And most of the stuff we didn't recover was sand. And so if you're drilling through sand, you're not going to recover anything. You're just pushing it out with the mud. Tons of core. So you can see the boxes full up. This is going to be hand drilled. So down here is going to be different. And I'll show you the difference in hand drill in a minute. This is going to be using the big drill. We've got a bunch of core. Hand drill over here was also quite successful in 2019. 2023, we had version 2.0 to the drill, upgraded it, brought it back, killed it, found glacial coral 19,600 years ago at 16 meters. So I was like, dude, I'm coming back here in 2024 and I'm going to crush it and get an LGM coral. And of course, I go out there and the fuel pump dies. So we didn't get to use drill 2.0 in 2024. But down here, I have a little graphic. And so when you think about this kind of stuff, we're really doing pin the tail on the donkey. We can't image inside the earth. We don't know what's down there. More holes is a higher chance of hitting these coral heads. They're anywhere from like, the size of this, what I did it earlier, the size of this to something that would be like from the edge of the table to here for a big one. And so you can imagine if you're drilling physically right here and that coral's right there, you're not going to hit it. But if you move that drill a couple meters over, you're going to hit it. And so you really got to poke a lot of holes to have a higher probability of pinning the tail on the donkey in order to get it, because you don't know where they are. They're buried under the surface. Unlike the hand drill, where it's a chainsaw with the little gear change on it. So we took the bar off and this actually drills a core. This is more like hunting for gold. And so when the fuel pump died due to the time of COVID, the Honda engine, just, poor QC, whatever, global shutdown. But we made hay while the sun was shining, and we went out and we just scoured the whole coastline and looked for this one species, that massive one, that Porites. And we cored as many as we could because, you get all the way out there. There's a whole bunch on that field trip that went wrong. But we still got a ton. And so if you look down here, you see that star. That was the 2023 trip. At around 16, 17 meters, it was 19,600. So we confirmed that this little CLEX model run in Excel was actually pretty good at predicting where that would be by drilling down over here below the surface. And so that's going to be our pin the tail on the donkey game using the land drill. And we recovered a really nice core that Rob worked on for his PhD 15,000 years ago. It was like, what was it, 2 meters? So well over like 160 years worth of stuff during the Heinrich event. And then up here on the surface is where we're searching for gold. And we did great in 2024. We haven't analyzed any of those yet because it just came back. But our drilling campaign, this is all the Vanuatu stuff. Pre-2019, when Fred went out a lot and then he and I both went out. We got a whole bunch of stuff here in this lighter blue. The orange is going to be a compilation of every group in the world who's done any tropical Pacific stuff up to 2015, a few more after that, but really nothing before about right here. Meanwhile, here's post-2019, where we just crushed it and just got tons of glacial coral that pretty much #1. And I will say that the stuff older than 15,000 years, these were only pieces to confirm that indeed the stuff was there. We don't have any cores. All of our cores, which are going to be what would make a climate time series, are kind of 15 and older. All right, only a couple minutes left. This is the same thing that I showed you for the Niño 3.4 in the other paper. We can do the same thing for the Southwest Pacific. And so this gives us, this is the target. We want to reconstruct this. Here in the Southwest Pacific, we can run it through the proxy system model and get some pseudo coral to compare to the coral data, which I will show you now. Well, we'll skip that. Well, it's just fancy statistics. It's 1121. I want to show the data. So it's fancy statistics to make sure that we can indeed record these force changes. And Rob did a ton of work. I don't want to minimize it, but we did some Monte Carlo simulation to show that indeed we can resolve, this one versus this one. And do you have 10 years? Do you have 50 years, 100 years? Play this game. But this is the piece de resistance. You're like, yay, that's it. There's a pile of data and a pile of work to reduce a whole bunch of stuff down to just one plot. But on the top is going to be the Southwest Pacific, so Vanuatu, and this is what I've already showed you before, Christmas Island. So this is the sweet spot to reconstruct ENSO, but all the data stops here. Here we had to do a whole lot of analysis to show that indeed we are reconstructing ENSO. But we see all these circles all the way out here, which Rob produced. And it's a pile of data, and it shows that down is weaker ENSO, up is stronger ENSO. And so for the most part, the coral data is showing the same sign as the model, showing a reduction in ENSO going back in time, but the model is underestimating the actual reduction in ENSO. And so what I mean by underestimating, here's going to be the median of the model output, and the coral data is always lower, and here's even much lower than the model output. So it's getting the right sign. The model is an older version. It's a lower resolution. Maybe it's not as good. Maybe we could use a better one. It's going to be really tough to get these corals out here. We talked about trying to go out there and drill in Christmas Island. But for sure, we have a whole bunch of stuff from all in here that just came back in 2023, 2024 to fill in more holes. But indeed, we are seeing weaker ENSO during the Ice Age. And because the power of corals to be able to resolve individual events, we actually found a way to define extreme events. In nature, we look at the observations in the Niño 3.4 index. So over 2 degrees, it's an extreme event. Well, the model runs a little hot. And for 018 in Vanuatu, there's no way to come up with a number in per mil space to say like, oh, that's an extreme event. So we ended up doing Rob did a whole bunch of analysis to show that we're using the 93rd percentile of the pre-industrial, whatever that threshold is, the 93rd percentile. It gives us a number of extreme events per century, and it actually turns out to be really close to observations. So we can then apply either in degree C in the model, or in 018 in the pseudocoral space, or in the coral for the modern coral, and get a threshold. And so over here, this is going to be from the model at Niño 3.4, 15 Ka. Here's the 93rd percentile. Nothing gets over it. ENSO's dead, no extreme events. Pre-industrial control, you can see these ones sticking up over here. So we get more extreme events, higher ENSO strength. And then at 2 times CO2, it's just like, pinging above it the whole time. And these are some random 300-year chunks here showing that during 2 times CO2, we get a pile more of extreme events. And we can do the same in the Southwest Pacific or in the Central Pacific for corals. Here's going to be that data. This is what I just showed you for the Niño 3.4. So this is our target. And it shows the change in standard deviation. So weaker ENSO over here, fewer El Nino events per century. So over here at 15 Ka, it's just like dead. ENSO's dead. There's no extreme events. Shut off. It's gone home. Over here is going to be our pre-industrial, where we kind of prescribed it to be at 0 and 7 by definition, 97th percentile, 93rd percentile. And then here's going to be 2 times CO2, where we're getting like 15 events per century and a much higher ENSO strength. Same thing where we have the model output for the Southwest Pacific and the coral data and the squares, and these are going to be the different time slices. And these triangles include that ocean circulation changes, the day after tomorrow stuff, because we have corals during then. And for the most part, we see the corals are down here. They're showing fewer extreme events. So fewer extreme events over here, weaker ENSO. And for the Southwest Pacific, we're still getting 15 events. And so there's kind of a couple things going on here. One, the reduction in Vanuatu is not as large as in Christmas due to pattern changes of ENSO, Vanuatu being outside the Niño 3.4. And you can even see it here. In the Central Equatorial Pacific, we're getting something like a 30% reduction in the pseudocoral and something in the teens in Vanuatu. So as we kind of expected that. And over here in the extreme events, we see, a reduction, a smaller reduction over here and fewer extreme events. But in Vanuatu, we still had the same amount in the future, which indicates that as ENSO gets stronger, it actually impacts more of the Pacific more. And as ENSO gets weaker, it impacts less of the Pacific, which was a pretty wild thing. But in general, the corals are agreeing pretty well with this model run under these different background conditions, suggesting weaker ENSO, fewer extreme events during these colder ice age periods. I'm not saying we can absolutely trust it for the future, but looks pretty damn good. Future work. So we just put in a proposal at NSF, which hopefully doesn't die in the next couple months. And it's looking at, this is the same data where the triangles are the Niño 3.4, that interannual stuff that I just showed you about, 2 to 7, 2 to 8 years, remember interannual. And then we did decadal. So we looked at the variability 8 to 100 years. And there's a wild relationship where during the last ice age, 21,000 years ago, the decadal variability was high. And then over here in the future, the decadal, the circle is below 0. The opposite happened where we had weaker ENSO during the last ice age, and it's going up in the future. And so we're like, holy cow, that's pretty wild. And you can see it over here in the power spectrum. You can look at the area under the curve where, you know, here's the ENSO band and here's going to be the decadal band. And the power is shifting from the last ice age, more decadal, less El Nino to in the future, kind of inverting, which has huge implications for the future. We'd have to worry less about decadal variability and more about interannual variability in 2 times CO2 world. So I put in a proposal to use more corals. Oh, did I update this? Yeah, I did update this. So these are all the different corals that we have, which are cores, which could produce climate records from Vanuatu, a pile of them going all the way back to 15,000 years ago. And then here are a bunch of stalagmites. Before this, I was collecting tons of stalagmites all over the Western Pacific. Turns out the stalagmites would be really good to record decadal variability. So the proposal was to say, hey, we're going to use these stalagmites from across the Western Pacific to see if we see more decadal variability during this ice age time, to then further test the model to see if indeed it is getting the variability right on the switch between decadal and interannual. 1129, take home. So in the alphabet soup of models, we picked one, a pretty good one, has realistic ENSO. It's showing stronger ENSO, more extreme events in the 2 times CO2 world. And we tested it back in time using all these different boundary conditions. It suggested weaker. We're seeing it in the corals, kind of lending some validity to that model over other ones. And the strength is really driven by these costly extreme El Nino events. And the model's predicting more El Nino events. And in the past, we're seeing this relationship hold such that if we do see stronger ENSO in a CO2 world, we could probably expect on that Taylor distribution of global GDP, more extreme events, which are going to be more costly. And then lastly, in the future, we're looking at decadal variability. Thank you, Anna Ruth. Does decadal vary inversely to interannual, which would be pretty neat if we could show that as well, like more credence to this model and help resource planners in the future. And with that, I will end at 11:30. Yes, and take any questions.
Thank you very much for the excellent, entertaining talk, Jud.
Who says science can't be entertaining?
So I want to take questions from students and postdoc first, if anyone has.
Don't be shy.
I really want to. That was a really fun talk. Thank you so much.
Thank you.
I have a question about, so like ENSO produces a whole bunch of other like global temperature and precipitation changes and stuff like that. Do any of like your data align with like other paleoclimate records in other parts that might show like droughts and stuff like that in like other global areas? I don't know. Yeah.
Great question. I think it's really hard for stalagmites, and I tried for years to find a stalagmite that will record ENSO. Like there's only a few that I know that are published that can resolve ENSO events, because when you put the water into the karst system, it kind of integrates the signal and you lose that sharp ENSO event. Marine sediments, they're in the ocean, so they're not going to give as much drought. They get some salinity changes. And if you have a high sed rate, maybe you can start to resolve this stuff. But it's IFA, individual forens, which is a costly analysis. So a lot of people usually do bulk. People are starting to do more and more. Really, tree rings are going to be the only thing which are going to do that. And going back to the glacial, you start to have floating chronologies, and they're working on tree ring atlases from all over now, especially like the Lamont group. And so like it's coming out. And so yeah, you just got to have trees back 20,000 years ago and nail the chronology. And You know what I mean? So it gets really difficult to get something which can resolve interannual variability and be that old, because as you go back in time, it's harder to find the samples, right? And so there's more samples from the last couple thousand years than 20,000 years ago. But yeah, that's a great question. I should look more into the tree meows.
Very cool. Thank you.
A question from
So yeah, thank you for the talk. Something that I was wondering, and I feel like I've heard some about is, do you think that there is any geographic, like, have you seen any geographic change in El Nino or La Nina, either in like past paleoclimate data or in future model runs? Do you see it shifting north or south, whatever?
Yeah, so there's different types of flavors, however you want to call it. Some people call it Central Pacific, Equatorial Pacific, EPCP. And so there's different flavors of ENSO. So not all ENSO events happen in exact the same spot. That's why I showed a composite for a whole bunch here. This is a composite. And so I've combined 3 events together. And this would be an EP event versus some weaker ones, which tend to have less warming over here and more warming over here. And so, and that's just due to the natural variability. Not all of them are extreme events. Some of them are weaker events. And so like, come on, too many animations. Where is it? Here. So there are some smaller events which don't quite get up to the extreme value that are the Central Pacific. And so just in terms of how ENSO operates, it has weak events and strong events, moderate events. And so we see that now without any sort of, well, one may argue that there could be forcing here, but even back here when the anthropogenic forcing was smaller, you still see these different events popping up. But going back in time, it's really hard to distinguish them using proxy data. And so that's why we kind of lowered our bar. And as opposed to trying to resolve these different type of events, we're just resolving like 30-year bends of stronger and weaker. And so like, and into the future, they're studying that because the climate models, you can resolve that and, you know, go bananas and produce all sorts of papers looking at the climate model output, looking at these different events. But going back in time, it's really hard to reconstruct those. And so for sure, people are looking at that in the modern and the future, but going back in time, you've got to really lower your expectations and, you know, go for a much more basic kind of, you know, lower bar for the reconstruction. But people are looking for the modern and the future for that.
Hi, I'm also using Fred's data from the Western Solomons. So maybe we can talk after the talk, but just a simple question. So what kind of other signals do you expect to see in paleocoral data sets? Like you're using different kinds of isotopes, but they're like a bunch of isotopes you can also use. So do you expect
Oh, are you working with Luke doing the carbon stuff?
exactly.
Yeah.
Postgrad.
Yeah, carbon isotopes. So when you run the carbonate powder through the mass spec, you get not only the oxygen isotope data, which is CaCO3, calcium carbonate, you also get the isotopes of carbon, the ratio of 12 to 13. And so there is a hypothesis that if you do have a rapid tectonic movement, a lot of times the carbon responds to, usually they say it's like amount of sunlight. So if it's a lot cloudier, then you have one carbon isotope over the other, but you could raise the coral up into the shallow waters and then also fractionate carbon differently. And so I think you're looking at that for relative land movements to reconstruct that. Yeah, maybe we could look at that in some of these corals and see if we can see some paleo seismic activities. That'd be pretty wild if we see some big step change. But it's also hard to resolve that with ENSO because in the Western Pacific, during a big El Nino event, you drop sea level in the Western Pacific, which also like increases the amount of sunlight coming through to the coral. And so I don't know, we'd have to figure out a way paleoclimatically to resolve ENSO events. Where is it? Here. So as this water cools, you can kind of think of it. So there's a gradient of sea surface temperature height normally, and during an El Nino event, the sea surface height goes like this. So it goes down over here and up over here. So if you have corals from over here and you do decrease that sea level, you'll get more sunlight coming in, which could possibly affect the carbon isotopes. And it'd be hard to separate that 15,000 years ago between that versus the relative land movement. But yeah, we could look into that. It'd be cool. Yeah, we should talk. Nice catch.
Thank you for a great talk. So the decadal variability of ENSO is considered as the PDO and or IPO, like the decadal variability on Pacific area.
Mhm.
So do we see the PDO or IPO variability using the coral data set?
Great question. Do we see decadal variability in the coral? Everything that I showed with the coral data, we actually pass it through a 9-year high pass. And so we actively filter out any decadal variability in the coral. Now, if after you do the 9-year high pass, you can still have decadal variability of the amplitude of the ENSO events, which could be a different component. But we kind of purposefully remove any of that variability because we don't want any of that variability to influence our ENSO reconstruction. And so there's the added caveat though, like when I showed when one samples the coral down the growth axis, if you do get off that growth axis, it actually adds decadal power to the reconstruction. And so how well you sample it, it doesn't affect the interannual as much as it does the decadal. And so it gets harder with the corals to do the decadal, which is why we're proposing to do the cave formations for the decadal variability, because that's kind of their wheelhouse. And so strengths and weaknesses to every proxy. And so we found it a little difficult, and you also need a really long coral record. And so it's harder to get over 30 years, and over 100 years is even harder. But with the cave formation, you can easily get a several 100-year record to look at the decadal variability. Good question though. We'd love to have a 600-year coral record. It's just really hard to do and expensive and time consuming. Any other questions? Oh, yeah. Can I read them? Oh, you read them out. I'll pretend like you're the asking. Oh!
So Marcy Perky Phillips had a couple of basic ones. One of them, I think, was in any given year, do we have either an El Nino or La Nina? And then the other question is does more extreme El Ninos also mean more extreme La Ninas?
Excellent questions, both. I kind of did gloss over that. So in any given year, we can either have an El Nino, which is up here, a La Nina, which is down, or normal neutral conditions in any given year. So it's one of those 3 states. And down are actually these big La Nina events. And nothing really hits that 2-degree mark. And so it's not symmetric about the plus minus for the La Nina events. And so like if you were strictly to say like, oh, if positive 2 degrees is an extreme El Nino, negative 2 must be an extreme La Nina. We haven't really had extreme La Ninas, but maybe there's a different threshold. This is like something that Yuko looks at. Or if you have multi-year La Ninas, that's actually a bigger whammo to the climate system than necessarily extreme. But these multi-year La Ninas really have a large impact. So it may not be as extreme, but prolonged.
And then we also had a question from Kurt Tollestrup, who asks, your plot showed the Vanuatu core sites have a few calendar gaps in your timeline. Is there any value to filling in the gaps so that all the dates in your timescale are available for analysis?
I would love to fill it all in. But if you look at the x-axis, which I kind of glossed over, I realized my intro was too long. I'll fix this. If I ever give this talk again, I'll fix that. These corals are maybe 30, 50, 60 years worth of data, and the x-axis is going back 15,000 years, 12,000 years, 9,000 years. And so you would really need like 1,000-year-long coral to fill it in, which they don't exist. They don't grow that big. And so we do have a whole lot more corals that we have collected to try to fill in the gaps, especially during these AMOC changes. And so we're actively working right now for a coral right around here, which is during the bowling Alarad. And so we have corals during the Heinrich 1 event when the AMOC circulation was pretty much off, and we have corals during the Younger Dryas when the AMOC circulation was reduced, sluggish. And we just recovered corals from the Bowling Alarod when the ice age was still in the ice age and AMOC circulation, this overturning circulation, was active. And so, yes, I would love to analyze all these, but it's laborious work. It's monotonous. It takes a long time. It's a lot of analyses to produce these records. So time and money. If we had more time and money and people, then yeah, we could fill in a whole lot more of the gaps. But go NSF. I don't know if you guys saw the news. The director resigned last night. Doge has been there since the 14th. Happy times. I kind of feel like we're the musicians playing on the Titanic as it goes down. We're still doing science, but it's like actively getting pulled out from under us. Anyhow, yes, Jack. Were there any more online questions, Costa? Okay, awesome.
Great talk, Jud.
Thanks, sir.
Good to see you haven't, been just sitting around, getting out in the field, torturing rocks. 2 questions. If we only have time for one, that's fine. The first one, I guess I'm trying to understand how the model incorporates long-term changes in the ocean. Like I would think since the LGM, just average, ocean temperature has changed and the currents have changed, and how do you deal with that?
So you want the model to be equilibrated to those conditions. And so going and running the time slices, you starts to leapfrog around. And so Pedro's really good about, he really started off, pioneered a lot of this. Where's that climate forcing one? Yeah, here. There it is. So depending upon where or what time period one wants to reconstruct will be what the precession values are, the eccentricity, the obliquity values are for that given time period, how big the ice sheet is. I think it was 5G reconstruction, how many greenhouse gases there are, because there's the ice core data to give you what the concentrations are, what the sea level is, depending upon where you are in time. And then the ocean circulation is what you're asking about. So normally what's done is the model is configured. So a lot of times it's leapfrogging around. And so let's say 0 Ka, it's run for CMIP and they have huge runs. And so it's really easy to go to 3 Ka and 6 Ka because you just change this orbital value. Then you let the model run and you monitor global temperature until it kind of equilibrates. And then from that, after the equilibration is when you start letting the model go and then accumulating that data for ENSO. And so you end up leapfrogging through time. And then for the LGM, you prescribe all the conditions and you just let it run until finally everything equilibrates and levels off. And then at that point is when you start to use the model output for climate analysis. So you let the model equilibrate. Spin up time, they call it, whatever. So you just let it run and monitor global temperature. And then 15, it's like, okay, we'll use LGM and get to 15. And then, you leapfrog, 0 gets to 9. And then like, what do you use for 12? Do you use 15 for 12 or 9? And so like you let the model spin up, which is an equilibration of usually global temperature. You can also look at AMOC values, the overturning circulation in some area if you're using the hosing until it levels off. And then you say, okay, the model is equilibrated under these conditions. Now let it run for hundreds of years to get the ENSO statistics. So it's people call it spin up. But the ocean circulation, you just let the model go. Like however it does it is how it does it.
Thanks. And the other one might be a quick one. Anybody ever tried to use some geophysics to map the corals in the subsurface so you're not playing pin the tail on a donkey?
Tough, dude. Even ground penetrating radar. It's such a hodgepodge of a mess. Like
that's what I was thinking probably the case.
Yeah, here, right? So you can imagine not only do you have, a big rock here and then, sediment infills these holes. And so you're going to have a whole lot of changes in density. And then it's like, okay, is this just consolidated reef rock? Because, the reef gets smashed by the waves. It breaks up the coral. All these bits fall down. They get cemented in. And then you can get a big hard rock of cemented reef rock, which is different from a coral head. But they could have kind of similar density. It's just resolving.
Yeah, I was thinking the domes, like you might be able to see those.
Maybe. I talked to Dallas and he was like, oh yeah, we can bring ground penetrating radar out there and try it. And I was like, it's a long way you saw where we had to go to get there. Like, I don't know, in a cost benefit analysis but I wanted to try it. All right, we lost people. Any other questions? If not, lunchtime?
Thank you very much again, and then we'll go out for a lunch after this.
Yeah.
So come to the lobby area on the first floor of the.
Thank you all for coming. Thank you for your attention.
Thank you.